There are two types of forces, active force and reactive force. Active force tend to set the particle in motion, and reactive force result from the constraint or supports and tend to prevent motion. So in simple words, a vehicle on motorway. So the engine is the active force, and the air resistance is the reactive force. I am standing on the ground. My weight acting downward is the active force. And what's preventing me from falling down or moving down is the reaction force from the ground. Okay? A fan on the ceiling, the fan weight is acting downward. That is the active force. And what's preventing it from falling is the connection with the ceiling. So that would be the reactive force. I've got that's not a very good uh, color. But anyway, it's exactly the same what I mentioned here. This is another example where a person is pushing, let us say, an object. So that is the active force, and the friction from the ground is the reactive force. So that's the active force, and this is the reactive force. The free body diagram. It's used to simplify things. There's a few examples here. Rocket, you got the free body diagram for it to get the calculations done. You got another one here. So basically, free body diagram, anywhere you do the analysis, looking at the application of forces on the system, you have to draw the free body diagram and then apply equation of equilibrium on it. Okay, free body diagram. Okay. Okay. Free body diagram. Okay, now the question I just mentioned, let me go back. I did mention, yes, I want to use this picture again. If this is in equilibrium, I did mention that every component, every particle on this is in equilibrium. So if I look at this part here, A ring, I know that the sum of all the forces acting on point A is equal to 0 because the point A is not moving. Okay. So remember this, if the system is in equilibrium, every part of it is in equilibrium. Look at this one. If I want to do the analysis on this part, only I need to find the analysis on there. I want to see the stresses on the drum. So I would just want to bucket. So I just want to do the analysis on this part only, not on the remaining of the crane. I know that the crane is not moving, so the cable is not moving, the crane is not moving, the bucket is not moving. So everything is in equilibrium. So I will just take this bucket first. So I draw a box around the bucket, and then I draw only the bucket and then look at the forces on the bucket. So basically, if I look at the force on the bucket, that is the weight acting downward and the tension force acting upward because of the rope. So there are only two forces. So the viewport diagram of the bucket would be something like this. That's W and that is my T. Now I've got simplified my problem. I can apply equation of equilibrium on this picture. Similarly, if you want to draw the Fibor diagram of you want to see the analysis, you want to do the analysis on point A ring. So you will draw a box or circle around the A and cut it off from the surrounding. So that's where so I will have O and this. So this is basically my ideal version of the picture, and then I will draw a Fibor diagram. So the Fibor diagram of the ring would be something like this. That would be my W. This would be my TB, and this would be my TC. That is my Fibor diagram. So remember, the whole structure here is in equilibrium. So every joint, every part is in equilibrium. So if I want to do analysis on any part, I will just cut that off from the surrounding and draw its free body diagram. If I had to do analysis on the actuator here, that's the actuator here, I would have cut it off from the surrounding. So that's my actuator. I would have cut it off from the surrounding and would have applied forces, draw its fiber diagram. So its fiber diagram is just simple 2 points. That's it. You got the force here and you got the force here. So remember, in simple words, if you got a big system and you want to do analysis on any one part, you cut it or cut that part off from the surrounding and then draw its free body diagram.